Welcome to part 2 of the tutorial on steady-state analysis. So we're just going to do right now a summary of sinusoidal steady-state, a general technique or recipe of how to tackle problems in the AC domain. So the first thing that you have to understand before you do any steady-state analysis, that this only applies to when the inputs are sinusoids. So if the inputs are not sinusoids, you shouldn't attempt to even apply these concepts dealing with steady-state analysis. Another thing is you have to know that we are assuming one of the following. We are assuming either the transient solution has decayed, or in other words, the steady-state solution is the dominant solution in the circuit. Or you might even assume that the transient solution has not yet decayed, but you don't care much for it. So this is basically an analysis that is focusing on the steady-state solution. Hence, it's called the sinusoidal steady-state analysis. So if these are the conditions, then you could apply this technique. And the general recipe and the idea behind and the mechanisms behind this technique is it uses a solution. You're assuming a general solution in the complex inputs as a complex exponential. So you're having e to the power j omega t plus phi, and this guy is, according to the Euler's formula, is cos omega t plus phi plus j sine omega t plus phi. I just want to remind you guys what's going on. You're assuming this is, initially you were given an input. This is the real input that we initially have. This is what the problem gives us. The problem is we have a sinusoid as an input, or as one of the, for example, the voltage source or current source could be a sinusoid of this form. Okay, this is what we have. And the problem is you're saying we can't solve this easily, so we generalize the problem to include a complex exponential. So we are simultaneously solving two sort of orthogonal problems, one of the cos and one of the sine, at the same time. And the reason for this is because the complex exponential is a very easy function to deal with, because it has very good derivatives, very good integrals. I mean, taking a derivative is just taking the coefficient of time and just multiplying it. Taking an integral with respect to time is just dividing the coefficient of time, taking the exponential, dividing it by the coefficient of time. And this is the idea. The idea is we can't solve this problem, we're just trying to solve this problem. So we solve this problem. Once we solve it, we realize during the applying the reverse superposition principle, we can take the real part of our solution, and hence we will get back this guy. So the idea is again, I just summarize it quickly. We can't solve this guy. We extend it to the complex exponential. We do what we have to do, then we come back. And this transformation of going to this domain, we call this going to the frequency domain, and then this domain coming back, we call it coming back to the time domain. And hence we deal with phases. So there's only, I don't know if you guys can tilt the camera to see this part. The tools that you need to know are very, very, very few formulas. You need to know, for example, how to convert a sine into a cos, and negative cos and negative sine to, again, in terms of cos. We call these like the cos basis functions. And the reason for this is because we're trying to solve, we're going to take the real part of something, of our inputs. So that's why we're transforming any of our sources into cos. That's the whole idea. So step one, when we deal with any steady-state analysis, like for example in this example, you see we have negative 120 sine 10t minus 15. Step one would be to convert all your your sources, your voltage sources or your current sources, into phasors. And before you can do that, even before you attempt to convert them to phasors, this is going to be maybe step two. The first thing is you want to convert everything to a common base using these formulas. So these are the three formulas that need to be memorized, or at least, you should be very, very familiar with. So in this case, we are given 120 sine 10t minus 15. So first step would be to convert this guy to equal to, using number 3, we just add 90 to the argument of the sinusoidal function. So you're going to get, this guy is equivalent to 120 cos 10t. You have minus 15, you've got minus 15, and you've got plus 90. And that brings it to 120 cos 10t plus 75. Okay, this is the first step. So if they give you, for example, if it had a negative cos, you'd apply this guy. And if the problem had this in terms of just a cos and there's a positive in the coefficient of the cos, then you would leave it as is. So the first step is to do this, always, for all your sources, if you've got a voltage source. And another thing is you have to make sure is that your frequency, your operating frequency, is indeed the same for the problem. If the problem has multiple frequencies, we'll deal with it differently. We'll use the principle of superposition, and if time permits, we could probably discuss that again. But we're assuming we're dealing with the same frequency. So we're assuming all the sources in the circuit, if there are multiple sources, they're operating in the same frequency. You have to check that to make sure they're operating in the same frequency. If they're not operating in the same frequency, just convert everything to the same basis, and make sure that you put aside a note that the frequencies are indeed different, so that you don't just go ahead and apply KVL or KCL as you would normally do with single frequency excitation cases. Another thing is, so once you do this, next step would be to convert your sinusoids into phasors. Now, again, a phasor is a complex number that represents the magnitude and the phase of a sinusoid. And it's very clear here. We've got a sinusoid with an amplitude of AM and a angular frequency of W, but we don't care about the W because, again, a phasor is just a complex number that represents the phase and the magnitude. AM is a magnitude, AM is a magnitude, shows up. The phase is, let's say, phi A. You realize a phasor has no knowledge of the temporal information of a sinusoid. It has no knowledge. And this is actually lurking in the back of our mind, that there is indeed an angular frequency. And in fact, it's very easy for any student to confuse a phasor, for example, with a complex number. An example of something that is not a phasor, but is indeed a complex number, would be impedance, which is the next step I'm going to talk about. So make sure that you don't confuse what a phasor is and what a complex number is. It's very easy to do so, to make that confusion. So when you're dealing with sinusoids, you're dealing with phasors. When you're dealing with anything else, talk about impedance, you're dealing with just a complex number. Realize a phasor and a complex number are the same thing, but when you're coming back from the frequency domain to the time domain, you're going to have to include the temporal information that you kept aside. But you don't do that with impedance. Impedance is just a number. It's not a function. Impedance is not a function. Okay? It's usually considered fixed for passive elements. Okay, so the next thing is now, once you convert all your voltage sources into phasors using just a very simple ingredient, just make sure you take the amplitude and the phase. And this is under the assumption that you have converted everything into the same basis function, which is indeed a cos. So if you had something in terms of a sine, you can't do this, and there's actually another technique on how to do it. You take the imaginary part, but that's not what we're concerned about this case, because we want to just follow the classical convention, and the convention is we take the real part. So use just the cos as the basis. Don't use a sine, just use the cos, and everything should be easy. Next step is to find the impedances of any impedances in the circuit. This is under the assumption that it has not already been given to you. Like, for example, if it was this case, I don't know if you can tell this, in this case, we have everything in terms of the impedance has already been given to us, like in terms of like values. There's no capacitive or inductive values. Everything has been given to us as impedance. If this is the problem that's given to you, you could easily skip this step. But if this has not been given to you, then you would need to do something. You would need to use these formulas to find the impedances of all your components in your circuit. So for the resistor, it doesn't change. The resistance is the same. For the capacitor, you'll have to do 1 over j omega c. So you will need to know the operating frequency or the excitation of the sinusoid in your circuit. And usually that is actually captured by the angular frequency omega. Now, sometimes in a problem, they could take it one step further and not provide you with the explicit value of omega. They can tell you that this circuit is operating on the excitation frequency in hertz. They can just give you, for example, something in terms of just hertz. And they're asking you, can you find the impedance in the circuit? And usually that's the first step. Or they can tell you to find maybe a voltage or a current in a circuit. But you can't do anything unless you know the angular frequency. But if they give you something in terms of hertz, you know you're not dealing with angular frequency. This is just a regular frequency. So you have to convert it to an angular frequency using 2 pi f. Very easy. So just use formula and you'll get something in angular frequency. This is under the assumption that they give you a frequency in terms of hertz. And this is actually, this omega equal 2 pi f is measured in rads per second. Another thing is they could give you the frequency, of course, explicitly, in hertz, you have to convert it to angular frequency using 2 pi f. If they give it to you as rads per second, that's fine, take it. If they don't give it to you explicitly, you could actually derive it from the argument of the sinusoids. For example, in this case, you could extract omega from the coefficient of time. So that's another way to find omega. So these are the 3 ways generally they can ask you to find, you need to find omega. There's, of course, a 4th technique, but I just don't want to get into it because that's just another problem of its own. If time allows us, we can discuss that. Another thing is when I previously talked about if, let's say, you had multiple frequencies, how would you deal with that? You would deal with them exactly how you would normally deal with single frequencies, but the only difference is you would consider every single frequency individually and sum up everything, the components, sum up the response in a specific, maybe reference point that you're considering in the circuit, and just add up all the responses individually. So you consider every circuit, every frequency response individually, but with the only difference that when you consider a specific frequency individually, you're going to have to kill other sources. And when I mean kill other sources, if let's say I've got a voltage source is killed by, you have to short it, right? And a current source, yes, a current source, you kill it by making it open. This is the recipe of how to use superposition, but I'm not going to get into that. And then another thing is, if you're dealing with DC, this is not AC, this is DC, that's why it's written in red. DC steady state, just make sure that you know that for a capacitor it's open, and for an inductor it's closed. This is the steady state sort of conditions of a capacitor and inductor. So for capacitor, it's always going to be open after some time because the capacitor is saturated, and for an inductor, the inductor becomes like a wire, becomes just closed. This is under DC steady state. And it can in fact be confirmed by AC steady state just by assuming omega is equal to 0 and applying using this formula. So if omega was equal to 0, where DC, the capacitor clearly has an impedance of J over omega. Omega is 0. Something divided by 0 is assumed to approach infinity. Something which has an impedance of infinity is indeed like an open, it's like the air. Okay? So this is DC. So DC is, we're assuming here is omega is equal to 0. And this is needed. This is, in fact, you might use this. This is very good to know when you're doing the transformation method. Okay? So I just don't want you guys to forget, to lose hindsight of why we're doing this technique, why it works. It works again because we're assuming the general solution, then we're taking back the real part. You have to realize this, and you should be aware of this, and you should be consciously considering this every time you apply this procedure, because some students may ask, why does it work? So you have to investigate the details. I'm going to cover that, but your book does a good job in exploring this, and I'm sure even your professor has covered this in great detail. Another thing is, again, you realize the inputs are indeed sinusoids. This does not work if, let's say, you had a triangular function or any other kind of function that was not indeed a sinusoid. This might not work. Of course, a special case of a sinusoid is indeed when omega is equal to 0, but that's a debatable issue. And then another thing is, we're assuming again, we have to assume that we are ignoring the transient solution, or the transient solution indeed decays after sufficient amount of time. Or you are assuming that you don't care for the transient solution, so you might not even care if it decays or not, but it will decay. The transient solution will decay, and this analysis again, I have to emphasize, it focuses on the steady state response. So the general solution is actually, it includes the steady state response and the transient response. It includes both of them, but we're ignoring the transient response because the steady state response dominates the circuit after some time t. This, you have to really understand this and really commit to this before you even do any of this stuff, because later if you assume that this is a general solution, or this is the only solution, then I told you somebody could ask about what happens to the initial conditions, and I told you the initial conditions belong to the transient solution, and that's why we don't deal with initial conditions. Okay, now we are ready to cover something called the Thevenin equivalences. It's just exactly how you did your DC analysis, just like the way you did DC, how you calculated the Norton and the Thevenin equivalences in DC. It's the same thing in AC. Just now the only difference is you're dealing with complex numbers. Okay, so let me just look at an example here. And somebody is asking you to find the Thevenin equivalency of this circuit as seen from terminal A And B, so A, somebody has to give you, when somebody gives you this kind of problem, the first question you have to ask is, what's the positive and what's the negative term? Because it does make a difference. We realize that potential, even current, and all these elements are indeed could be seen as kind of like vectors, because the direction matters. I mean, the reference matters. If you told me this is A plus and this is A minus, and you change this, it's a different problem. So we're going to assume A plus and this is A minus. This is the first thing. And usually it's going to be provided in the problem. The second thing, when you look at this problem, is, let's say the problem was given to you as this. I told you, if they gave you the problem as a negative sign, you would use these formulas to reduce the sinusoid in terms of a common base where you're using cos as your basis function. That's the first step. Second step, you convert the cos into a phasor, as we did here. Very easy. You just take the amplitude comes here. You take the phase, forget about the temporal information for now. The phase is 75, it comes here. Again, what's lurking in the back of our mind is omega is 10. We have to put this down. This might be something, maybe you might think it's a simple step, but when you're dealing with multiple frequencies, this can get confusing. So you have to be conscious of the fact that omega is equal to 10. Now, your sinusoid is indeed now a complex number. Just like the way any of your impedances are complex numbers. You're going to treat everything just like the way you dealt with DC. The only difference is now you're dealing with complex numbers as opposed to dealing with regular numbers. It's the same thing. Now, this is now a reduced problem. Now you can do anything that you did with the DC, you can do it with this. The only difference is using complex numbers. And it's not even a difficult thing because your calculator can now deal with all the operations, the complex number operations, multiplication, division, conjugate, and all that kind of stuff. Okay, I don't know if a calculator can do conjugate, but maybe it could. Next step. So you've reduced your circuit in terms of, you're right now in the phasor domain. Realize this solution is simultaneously tackling the problem if there was an input as a cos and an input as a sine, which are orthogonal and are not interfering with each other. This solution is a solution right now that you're dealing with the complex exponential. You will have to come back to a time domain for you to solve the original problem, which were given cos. You see, the original problem was a cos. A cos is a real function. Okay, so here now we're in the phasor domain. Once you convert everything to phasor domain, the question is, how do you find the impedances? You find the impedances using any of these formulas. So, for the resistor, it doesn't change. This is the 4 ohm goes to 4 ohm. How do you find the impedance of an inductor? If the impedance of an inductor is j omega L. J is seen here. Omega L is 10 times 1.2 Henry gives a 12. And then for the capacitor, it's just 1 over j omega C, or another way of saying it is negative j over omega C. Omega is 10 times, okay, is there any problem here? Do you have a problem? That's the question. It was 60 farads, 1 over, I don't know, can you guys just verify this? Is it true that if you take a 60 farad capacitor, you'll get that? Or is there something wrong? Because I don't think that's right. Is it? No. So so what would this have to be?
1 over 60 times 10.
1 over 60?
1 over 60 times 10.
Yeah, so
600. 1 over 600.
1 over 600? Okay, let's see. 1 over 600. No, I want this to be in farads. Is it true? It's going to be 1 over 600?
Oh, you want to convert back?
Yeah, that's right. That's right. I want to know. I want to know what this guy is, because I want to solve this problem. What would this be? It's just a problem here. What does this capacitor have to be for this transformation to be consistent? That's the question I'm asking. What does this guy have to be? It should be a decimal number. I expect it. I mean, it's very easy. What I'm asking is very simple. It's just basically I'm just saying what is you're given negative 6j is equal to negative j over omega is what? 10c. So exactly 1 over 60. 1 over 60. And this is farads. So we're given this is a problem. What's going on? Okay, so this is a problem that was given to us. So again, we have a farad of 1 over 60, which is some value. We take it, we multiply it by the operating frequency, the angular operating frequency, measured in rads per second, multiplied, find the reciprocal, you indeed find negative 6j. There's a negative that comes from the top. So you got negative j over omega c. So once you commit this to memory, everything becomes easy. Now you've transformed the problem with the equivalent impedances in the phasor domain, and now you're able to do any kind of analysis. Now, the question that we're being asked is not to find a voltage or a current or anything. We're told the topic of today is finding the Thevenin and Norton equivalency of a circuit, and to apply maybe one iteration of the transformation technique to transform between Thevenin and Norton. And if you're able to do even one iteration of the transformation, you can apply it iteratively to a circuit that is indeed convenient and apply the transformation technique, just like the way you did under DC. So the problem is given to us as here. So we've taken the problem from the time domain, we've gone now into the phasor domain, and now we're asked to find the Thevenin equivalency of the circuit as seen from terminal A and B. That's the question that's being asked to us. So how would we do this? Well, for Thevenin equivalency, let's talk about Thevenin. The idea is very, very simple. Let's just say you're trying to find a Z Thevenin. Okay? What you do is you kill all, I don't want to use this word, kill. Okay, so let's use, okay, you turn off all your sources. And these sources I'm talking about are independent sources. You turn off all your independent sources in the phasor domain. Just like the way you did under DC, you just have to do the same thing. And how do you turn off your sources? So for example, a current source. Does anybody have any suggestion? How do you turn off a current source? Current source? Current source is open. Current source is open. Voltage source. Exactly. You kill a current source, but you make it open, and a voltage source, you make it open. And the logic behind this is very, very simple. The reason why this is actually make it closed. This is a big mistake. Yeah, this is short. Short or closed means the same thing. Just short it. Let's use this word. Just short. Let's short the circuit. Okay? And the logic behind this is very, very simple. If let's say you have a current and a current source that's going through, let's say, I want to make it very simple. So if let's say we have a current source that's going like this, we realize that current is flowing. So the only way for us to get rid of the current, we don't want any more current to go through, is you have to get rid of it. That's the only way. That's why the only way to kill a current source is to actually plug it out of the system, to remove it. But a voltage source is a bit different. When you have a voltage source is actually providing a potential difference across some terminal AB. So the best way to kill a voltage source is to make sure that the potentials are the same. And the best way to make the potential the same is just to connect a wire through them. Hence the potential is the same. That's why we short voltage sources. Very easy technique, very simple, very intuitive. And in fact, you don't even have to memorize this. Just apply logic every time you present with the same problem. This is a technique. This is a recipe. So we're going to apply this to this. If you have any questions, just stop me, because we're not covering much today. It's just, we're almost even done. After this is just the power transformation principle. Average, to find average power, maximum average power. So applying what we just discussed, how would we find the Thevenin equivalency as seen from terminal A and B? That's the question that I'm asking. How would we do that? So I just gave you guys the information. I guess you guys now to tell me what would I do to this circuit? Short what? Yeah, I have to short the voltage source, because I guess we just discussed that. So we take this if this voltage source was not a voltage source, was indeed a current source, what would we have to do? What would we have to do? We have to open line. So open line meaning if this was here, we would just let go of it. Right? We would just have nothing that connects this. But in this case, we were told to short it. So to short this circuit, what you're doing is basically what you're saying is, let me just write this in red. What you're saying, I don't know if this angle is pointing well, but what you're saying is this. We're just basically saying, let us connect a wire, because that's what a short is. We're going to connect a wire and get rid of the voltage source. That's what you're doing. You're just connecting a wire. So I'm going to do that, but I'm not going to interfere with the original problem, so you don't see what, you don't lose what we saw. I mean, so here, this is plus, this is minus, this is 120/75, and then you have this. You have this, sorry, this guy was killed. So you have this. Okay, and then we have what? Remember, this is the wire that is coming as a result of killing, sorry, of eliminating the voltage source. So this is why this wire comes in the picture. And then the A, I'm just going to take the A component, I mean the A reference, I'm just going to flip it to the left so you guys can see what's going on. I mean, I've not changed the problem, I've just turned the wire over so you guys can see what's going on. So you've got A, you've got B, this was still, nothing has changed, 6J, 4 ohm, 8 ohm, and 12J impedance of the inductor. Okay, so we'll give it, this is a problem. There's now, you realize the problem has no voltage. And this is in fact a check. Whenever you're finding the Thevenin impedance, you realize you don't have to have any sources. If you have any active sources, you know you're doing the wrong thing. Okay, this is a rule I have to say again. If you're finding the voltage, if you're doing the Thevenin impedance, make sure you have no sources. Voltage or current, they should not be in the circuit before you proceed. So now we know there's no voltage sources and have substituted, in fact, this voltage source for a wire that is actually a short, that is shorting this terminal, hence presented by this line. So this is the previous voltage source where it exists, and this wire actually exists. And I cannot just continue the problem by just eliminating it. This has to be there, otherwise you change the problem completely. Okay, so now the question is, we're trying to find the Thevenin equivalency as seen from reference point A and B, and we still haven't solved the problem. And the question is now, we need to somehow do a sort of a visual transformation for this problem, because it's difficult to see. Some people can see it, some people can't. So I'm just going to try to make it much more easier. This guy is equivalent of this. Okay. Okay, we have capacitor. We have, yeah, and then, I don't know if you guys can see this. Okay, this doesn't look that good. So this is, I'm going to try to make it very much more explicit. Let's use sharp, sort of a triangular representation for the resistance, so you don't confuse it for the inductor. Okay, so now you realize this is still terminal A, this is terminal B. I want you guys to just look at this for a second and see indeed these two things are indeed equivalent. So this is going to be minus 6, J is going to be 4 ohm, this is going to be 8 ohm, and this is going to be 12J. Okay, so this is the equivalency. So you guys just take some moment and see that these two are indeed the same. I mean, what has really been done is I just took this terminal and I stretched it. I stretched it like like a band. I stretched this guy here, and this guy came on top. This guy came on top, and then I stretched this guy. I stretched this guy, and I realized that this guy is a connection that's in between. This guy is really indeed this guy with this guy combined. I mean, you realize a wire that looks like this is the same, is equivalent as this, as a wire, as a component wire. If this is a wire that's connected like this, I mean the voltage share, the voltage share, the voltage share, the voltage share, the voltage share of this anywhere in this wire is going to be the same. So if we substitute for a straight wire, it's the same. So this terminal that you see here might be confusing, but it just came as a result of connecting this wire, maybe this component, this wire from here, and this wire from here to here. That's where this came from. But now this is more visually appealing than that. So now that we are seeing that we have reduced this to this, and I want you guys now to tell me what the impedance as, let us make things easier. Let us say this guy and this guy, let's say we reduce the circuit to something like this. Let's call this Z1. Let's call this what? Z2. And this is what? B. This is A. See, things become easier when you just take a complex problem and try to tackle one thing at a time. Make it much more easier to see, then go from this to this. So this is now very, very easy to see. This is now a standard 2-series impedance problem. Okay, analogous to the standard 2-series problem, 2 resistance in series problem. Same thing. Now, the question is, how do you do this? How do you solve this? This is a problem that I'm asking you guys. What's Z1? It's what? It's okay. Let me ask you. Okay, let me ask you. Is this one component and this is another component, right? We can treat this guy as one component exactly. So they're in parallel. That's right. So what's Z1? I don't need an exact answer. I just want like the technique. What is Z1? As you see, the question is that you could tell me anything. That doesn't make a difference. The concept is what really counts. What's the technique? What's the formula?
-6j parallel with.
That's right. You're right about it. You said -6j in parallel with what? With 8 ohm. This is true. What is a fast way to do this?
8 ohm multiplied minus 6j over minus 6j plus 8 ohm.
That's exactly right. And she actually extended the problem under DC. Under DC, remember we told the resistance in parallel for 2 resistors R1 and 2 is equal to R1 R2 over R1 plus R2. The same thing can be extended to impedances. So of R, we substitute for Z. So it's the same thing. So the Z, again, this is an abuse of notation, but please excuse it. So you get Z1, Z2 over Z1 plus Z2. That's exactly what we do. Same thing. Nothing changes. So she suggested the right solution. The solution would be -J into 8 ohm. And I'm just going to get rid of the units ohm for now because we know that. But this is not the final answer. We're still in the phase domain. So -6j plus 8. You realize that unlike the resistance that you dealt with in the DC case where the resistance were all assumed to be positive values, here, you see, we're allowed to have a negative. Don't, in your mind, interfere with the problem and get rid of the negative. Don't do that. Leave the negative as is. This means something. And that's actually the right impedance of this component right here. Now that we do the same thing, let's apply it. Now I want you guys all to give me what Z2 would be. What's the value of Z2? Just like the way you did here. I just want just an answer, just like what you did there. So what would be Z2? Yeah, 12j times 4, right? Over what? 12j plus 4. And this is exactly what you do. Now, once you found Z1 and once you found Z2, the question is, what's now the accumulative impedance as seen from A and B? Does anybody can give me a formula in terms of Z1 and Z2? Don't forget about the numbers. What you did B? What's the impedance as seen from reference A and B? What did it be? Exactly, Z1 plus Z2 because they are in series, right? So it would be Z1 plus Z2. That's right. So how would you, now that you know it's Z1 plus Z2, this is just numbers. Just plug this into a calculator. You're going to get, I believe, a value of, so Z1, first of all, is going to be, this guy I believe is going to be equal to, I don't know if you guys can see this, 2.88 minus 3.84 J. And this guy, let me just take this guy aside, Z2 is going to equal to, I believe, I know you guys can confirm this, 3.6 plus 1.2 J. That's right? Okay. So after this step, we found what Z1 and Z2 is as numbers. So basically, as we add complex numbers, we add the individual components. So you add the 2.8 minus 3.6 and negative 3.84J and the 2J, and you'll get an answer of, I believe, you're going to get an answer as, so the impedance as seen from terminal A and B, Z1 plus Z2 is going to be indeed is going to be indeed 6.48 minus 2.64 J. That's the impedance. This is a complex number, that's fine. Now, we call this guy Z Thevenin. We actually found right now what Z Thevenin is. So just to recap real quick, they present you the problem. If it's not in the phasor domain, converting the phasor domain using what we just previously discussed. To find the Thevenin equivalency, you have to find first of all the Z Thevenin, which is again, which would be, okay, you have the Z Thevenin. To find it is you have to kill your voltage sources or your current sources. To kill a voltage source, make sure that you make it a short. To kill a current source, make sure you make it an open. And do that, apply regular impedance reduction techniques using elements in parallel, in series, element by element, elements in pairs to get it done. This is just a recap. Okay. Next. Now that we found what the Z Thevenin is, the next question is going to be asked, what is the V Thevenin? Okay, so I'm just going to put this aside. This is the V, we just found that this is going to be the Z Thevenin. That's a Z Thevenin. The question is, next question is, what is the voltage Thevenin? Thevenin voltage as seen from terminal A and B. So you're trying to find out, the next step is, what is the equivalent voltage as seen from terminal A and B? The question is, do we kill voltage and current sources when you're trying to find V Thevenin? That's the question I'm asking you guys. No. If you did that, what would you get if you did that actually? You say, what are you doing? There's nothing, there's no voltage. Yeah, there's no source of energy. Exactly. So for this one, the problem is, I'm just going to use the same picture because I want to save time. So we want to find the voltage, Thevenin voltage. So to do this is very, very easy. I mean, look at this and you say, okay, you can apply many techniques. You can apply Ohm's law if you want to go with the fundamentals. You can apply Ohm's law. And how would you apply Ohm's law is just basically saying, hey, I know the voltage that's here. I can find the current that goes through here. I can find this current, let's call it I1, and I can find the current that goes through here. Let's call this I2. If you want to use Ohm's law, very easy. You know the voltage is here, and you know the voltage, we assume a reference of 0, for example. So you would know how to find the current that goes through here, because these two impedances can be treated as one impedance, or you can treat it as two individual impedances in series. It doesn't make a difference. The equivalent is the sum. So you can find this current using V equal IR. I'm using phasor notation, so you don't confuse it with DC. So to find I1 is going to be this V divided by the equivalent impedance, and this should be Z actually. So you'll find it, so I1 would be, let me just write this down, I1 would be 120/75. You realize this is a complex number, eh? Now, for now, this is a complex number. And divided by what? Divided by the equivalent impedance. The equivalent impedance is -6J plus 8 ohm. Just do that and you'll find I1. Likewise, you can find I2. I2 is the same thing, 120/75 degrees divided by 4 ohm and 12 plus 12J. You can do this technique. Once you find what I1 and I2 are, then now it's very easy to find what VA and VB is. You realize when you're doing the voltage, finding the Thevenin voltage is just like finding the regular voltage, but the only difference is usually the voltages terminals or injection points could be very far from each other. So you're basically applying the sort of the KCL or KVL twice. You'll see. I mean, naturally, it's like applying a problem twice, because you're finding a voltage at two different places. Okay? So in this case, the voltage at terminal A can be found very easily by taking the current that flows through here and stepping it up. So basically, the current times 8 ohm will give me the voltage relative to 0. So for example, another way to say this is VA minus V0 is equal to I1 times the 8 ohm resistance. Times, actually. I don't know if you guys see this. Let me write this down again. It's true to say that the voltage here is 0, right? VA minus 0 is equal to 8 ohm times what? 8 ohm times I1. This is a true statement because I know that the voltage here is 0. The voltage here is VA, and I know for sure that this is a high value. I know that the current is coming down, so I'm just stepping it up. I'm just saying, hey, if I take the current and I multiply by 8, I get 0 because V equal IR. This is true. That's a true statement. This is using Ohm's law. And you can do the same thing. You can say VB is VB minus 0, which is the same as VB, is equal to the current that's flowing through, which is I2 times 12J. And then once you find this, you can find the value of VA and VB because I1 and I2 are actually numbers given to us. So you can multiply this by 8. You take this guy as a value, complex number, multiplied by 12J, and you'll get what VB is. And hence, if you know what VA and VB is, the Thevenin voltage is going to be VA minus VB. This is approach number 1. This is using Ohm's law. If you don't want to use Ohm's law, for example, you could apply KCL, which is another technique. Another technique is using KCL. KCL, you say, you know what? Let me find what is let's apply KCL at node A. How do you do KCL at node A? I need you guys to give me that answer. How do you do KCL at node A? It's just a two element relation. What's KCL at VA? Can you guys tell me? What would be KCL? Anybody want to give? Tell me what KCL at VA is. Any tip? Anyone? No idea? Okay, KCL at VA is VA minus what? Minus 120, 75 degrees. What's that? Over minus 6J, right? Over minus 6J is equal to VA minus what? We made this our reference. 0. Divided by what? 8 ohm. And you can now solve for VA very easily. Now in this case, you don't have to deal with the currents that went through. Just apply it. Apply this formula, collect VA. It's very easy. Take the VA on this side and factor. So for example, if I was to do this, I would say it's VA, I factor, I have 1 over minus 6J minus 1 over 8 ohm, I believe. Why? VA minus 120, no.
VA minus 120 over negative 6J plus VA minus 0 over 8. But you could on the other side of the equal sign.
You're actually right. Thank you for pointing that out. This is true. See, this is good. When you guys are awake, this is good. He's right about that. You say VA minus this guy divided by this guy plus VA minus this guy divided by this guy is equal to 0. You're 100% right about that. I was thinking of something else. There's another technique without using this technique. Another technique would be to say this guy minus this guy divided by this guy is the same as this guy minus this guy divided by this guy by the negative. Right? No, by the negative because you're saying is equal to. You're right, because you're saying the current that's going through, the voltage, the current that's going through here is the same as the current that's going through here. But if you don't want, it's best not to look at it that way. He's right. The best way to do it is just to say VA. If you're using this point, you're saying VA minus this guy. You see, let me just make it very clear which are the two techniques. You can say VA minus, let's call this Vx, for example. You can say VA minus Vx over minus 6, for example, plus VA minus 0 over 8 ohm. This is the standard procedure. Another way to look at it is to say the current that's going through here is the same as the current that's going through here. So you could even say, for example, Vx minus VA over minus 6. You see, you're saying the current that's going through here is the same as the current that's going through. Now you can use the equivalency is equal to VA minus 0 over 8 ohm. You realize these two are the same. Why are they the same? Because if I take this guy and if I take this guy and I bring him over, if I take this component and I bring him over, it's going to be minus Vx minus VA over minus 6, right? And this now, exactly, minus 6J, right? Minus 6J. So if you take this negative, what happens is negative? This negative can come in. So you have what? A negative here, and you have a plus. Right? Now this makes sense. VA minus Vx over 6, hence the equivalent. So there's two kinds of mentalities how to think about it. You can say the current that goes through here is the same as the current that goes through here. Or if you don't want to think about like the signs and this kind of like analogy, just say, you know what, go with the classical technique that he proposed, which is the best. Just go VA minus whatever the voltage share divided by 6 plus, forget about equal, plus VA minus this divided by this divided by 8 is equal to 0. And I actually recommend this because this actually can work for multiple connections. So this is the best technique to memorize. Okay, that's very good, Greg. Okay, yeah, so you can solve for VA using this technique. And the same thing, let's find what's the KCL as seen from as seen at node B. How would you guys do it? Any suggestions? Same thing. VB minus 120, 75 degrees over 4 plus VB minus 0 over 12J is equal to 0. This is, and then you can solve for VB. Once you find VA and once we find VB, that's very good. Let's say now, if you apply this technique or even the technique before using Ohm's law, and there's also other techniques. You can also use mesh. In fact, mesh is actually quite convenient for this case because we have a voltage source. And mesh analysis is basically using KVL. And KVL, you talk about the voltage across a loop is 0. Hence, you have a voltage source. So it's good. You can use this voltage source and you can apply I1, for example, apply I2, and you can do the same thing. At least for I1, you could do it minus I2. Yeah, you could do it under, is it possible? Actually, I don't know. If it's, in this case, is it possible? Yeah, in fact, you could even reduce. You could reduce the circuit. Have to think about that. So KCL does the job. Ohm's law does the job, for sure. Okay, KCL does the job. KVL, and hence node analysis will also do the job. Okay, let's just proceed. So when you do that, you'll find your VA minus VB is indeed equal to. Yeah, you'll find out that when you sum up, you find your VA, you're gonna get. Okay, if you apply the Ohm's law before, because that's the solution I have, you will get 8I1 minus 12J I2 that we discussed before is equal to, which is the same. This is equal to V Thevenin, which is equal to VA minus VB. You could check. It's equal to 96 angle 111.87 degrees, I believe. I may be wrong. I'm just checking. No, this cannot be true. In fact, it should be this minus 113.83 angle 93.43. So ultimately, it's equal to 37.95 angle 220.31 degrees. This is your final V Thevenin. Okay. In fact, I'm going to even write our answer as yeah. Is it okay? Can you guys give me the Cartesian coordinate of this? I mean, representation of this complex number. What do you guys have? What do you guys get when you do this? Do 37.5 cos this and 37.5 sine this. What do you guys get? Does anybody have an idea of what the value of that is going to be? What are you guys getting? Yeah, Cartesian coordinates. I'm just converting now the polar to Cartesian coordinates. You get negative 28? Negative 28, uh-huh. 0.938 and? Minus 24.55J. So that means we have a big problem. You're not getting, Oh yeah, no, I'm seeing a completely different thing here. Let's forget about this. This is, I don't know why you guys are getting these values. There's some conflicting answer I'm getting here. 2.88J and 3.66 Z Thevenin. Yeah, so this is true actually. You're right, this is true. This actually has to be true. And this is, you're right, this is true. I'm convinced this is a true answer. Anyway, this is the voltage. Let's leave it as this for now. Okay, this is true. Now the question is, if they asked you to convert the Thevenin voltage and represent it in the time domain, how would you do that? So we got this to be our V Thevenin, and we got our Z Thevenin to be this guy. Okay. So graphically, what's going on is we have a terminal. For example, we have a voltage. We have to now represent a voltage source. So voltage source, right? And this voltage source is V Thevenin, by the way. So we've got V Thevenin. And you go here, and what do you have here? What's this guy called? What's this guy called? We call this guy what? Z Thevenin. And then we have the load A and B, right? And this is the equivalency of this circuit. We have basically reduced all this problem into this. V Thevenin equivalency, I mean in series with the Z Thevenin. And the V Thevenin, we found it to be 36.95 to 20 degrees. And the Z Thevenin, I don't know, was gotten to be.
Do you want 36 or 37? Because you have 37.95 and then you have 36.95.
No, 37.95. 37.95. That's something else. 37.95. That's what you get. And then the Z Thevenin you get to be equal to. I don't have it in complex numbers. I don't have it in polar coordinates, but it's the same thing. The Z is equal to 6.48 plus 2.64 J. Just confirm. You guys get the chance. Anyway, so that's what we have. This is our circuit. So we have actually reduced the problem into its Thevenin equivalency, as seen here in the circuit. Okay, makes sense. Now the next question is, can we find the Norton equivalency of this circuit? And that's not a complicated thing to do. To convert Thevenin equivalency to a Norton equivalency, all we have to do is just one iteration of the transformation technique. The transformation technique tells us if you have a voltage source in series with an impedance, to transform it into under one iteration, you would have to take the change of voltage source into a current source, and that relationship is easily using the Ohm's law. V is equal to IR. So the change of voltage source in the current source, you take the voltage source and divide it by the equivalent impedance, which in this case is going to be the Z Thevenin. So another way of saying it is Z Thevenin is indeed equal to Z Norton. They're the same thing. So you just take the V Thevenin divided by the Z Thevenin to find the I Norton, and then you would take the Z Thevenin or the Z Norton, doesn't make a difference, they're both equal, and you take it and make it in parallel. So for you to see that, this guy is the equivalent of I Norton, okay? And then what do? We take it, and it has to be, the Z Thevenin has to be in series, and it doesn't make it. I'm just going to use the word Z Thevenin slash. No, slash isn't a good thing because you might think it's divide. It could be either, this is either Z Thevenin, or it's the same thing as Z, which is equal to Z Norton. So I'm going to put Z Norton here, just for consistency. And you have this, and then now you have the load. So again, you can go from the Thevenin equivalency to the Norton equivalency using this technique. And you can even go back. And this procedure of taking an equivalency in this type and transforming to this is called the transformation technique. So we're killing two birds with one stone. Okay, so in this case, what's the I Norton? And you guys to tell me, because I just said it right now. What's I? It's going to be what? What is this guy going to be equal to? It's going to equal to what? To V?
37.95 angle 220.
Okay, that's right.
Divided by 6.48 plus 2.64 J.
Excellent. So you use even this Z. you're 100% right. So it's going to be 37.95 to 20 divided by the Z7, which was 6.48. This is going to look very bad on the camera. You'll have to just get rid of this. Okay, so the Thevenin equivalency. This current, this I, is, I don't know if the camera can capture this, but it's going to be, again, V Thevenin divided by Z Thevenin. And I'm not going to write down the actual number of values because it's obvious. V Thevenin is this value, and the Z Thevenin is going to be Z Thevenin. Always Z Thevenin and Z Norton are always the same value. So you shouldn't be, that's not a big problem. So this transformation is very easy. And then you find A and B. So you have covered transformation, Norton, Thevenin, summary of AC. Now we need to cover the maximum power transfer principle. Okay. Okay. Okay, maximum power principle. So, if you, let's say you take a circuit, and then let's call load impedance. What do I mean by load impedance? I don't remember if you guys remember in the circuit that we had before. Let us consider the Thevenin equivalency. So let's say we had a V Thevenin. Everything is indeed in complex numbers, okay? Everything is indeed in complex numbers, and then you have something like this, okay? You have, what's this guy called? It's going to be a Z Thevenin, for example. This could still be applied to the Norton representation, but it's the same thing. So if you go here, and you go here, and then here, this guy is called, we'll call this guy the Z load, or the load impedance, the Thevenin impedance, the Thevenin voltage, okay? And the question is this is what power maximization is all about. It's saying our free parameters is the load impedance. And the question is, usually the Thevenin impedance is given to us. It's beyond our control. It's how the circuit is behaving. This is the activity in the circuit. And the question is, this is activity in the circuit. The question is, we want to draw, this is a network. Let's call this maybe a power network, okay? A network, okay? And the question is, what can I adjust my load parameters such that I can maximize power from this network? Maybe. This is a typical example. The V Thevenin is activity in the network. The Z Thevenin is the equivalent load in the network. So this is basically a representation of some network, and you don't even care. It's like a black box. And the question is, how much power can I extract from this network? That's a question somebody's asking you. So the only thing that's within your control is a Z load, or your load impedance. It's the only parameter that you can control. Under the DC case, we're not dealing with ZL, we're dealing with RL. And we basically differentiated the optimization function with respect to the load. I realized that if our RL is equal to our Thevenin, R Thevenin, this is under DC, this is DC. We realize this optimized the power consumption. We could extract maximum power from the circuit, a maximum average power if we have this. And I'm using the word averages because we're dealing with sinusoids. Okay, so this is what we have. So in this case, under DC, we didn't use the word average, we just use power, maximum power. But on the AC, because things oscillate, we're saying, and which still applies when omega is equal to 0, is saying RL has to be equal R Thevenin in this case. Okay? Now, the optimization problem was taking a derivative with respect to L. With respect to RL, take a derivative, set it equal to 0, found a critical point, and we found out that RL is equal to R Thevenin. This is the result of the optimization problem. But under AC, it becomes a two-dimensional optimization problem. We are now taking the derivative of the optimization function, whatever that is, actually it can be derived. It's very easy to do that, but in the interest of saving time, we're going to cover that. But it says we're taking a derivative with respect to the resistance, and we're taking a derivative with respect to the reactance. Again, the reactance is indeed the imaginary part of the impedance, of the load impedance. And we found out that when we did this, when we took the two-dimensional derivative with respect to resistance and reactance, we found out that indeed, I'm not going to go through the derivation, but we find out that indeed that your R Thevenin, because let me write this down very clearly. Z Thevenin is equal to R Thevenin plus J, maybe let me use plus Jx Thevenin. What does this mean? X is just the reactance. Could be a positive, negative value. Okay, it's just if it's a positive value, it's inductive. If it's a negative value, it's capacitive, and R is just a regular resistance. This is the general form of Z Thevenin. And also Z load can also have something, the same thing. It can be represented as RL plus JXL. This is also how we can represent the load impedance. Now the question is, when you solve this, I told you this two-dimensional optimization problem, you find out that the DC case still holds. You find out that to maximize power transfer, you have to have R Thevenin is equal to what? RL. This is the first step, and it's actually consistent under the DC case. Fine. But again, under the AC case, we're dealing with a complex, we're dealing with a complex number, which is a two-dimensional sort of entity. So we have to consider the reactance, which was 0 under the DC case, but now not anymore. So now what is it? So you will find out that if you do the optimization problem, you find out that X Thevenin is equal to negative XL. This is actually the optimization condition required to draw the maximum power, average power from a network. This is the condition. Under this condition, then you can draw maximum power. If this does not suffice, if this does not even hold, if even this is changed a little bit, that's not true. And the reason for this, you'll realize naturally, is that if XL and X Thevenin are the negative of each other, you can sense a cancellation, because realizing you're having an impedance in series. So the X Thevenin and the XL are going to what? Cancel each other. So the imaginary component of the power of the load is killed. And that has to tell you a lot to do with something imaginary power. What you're doing is we are transforming, this is just analogous to transforming all the complex power into purely real power. That's why this condition actually exists. In fact, if somebody did not even do the the optimization problem and has a sense of what the power could be imaginary, could be real, and both domain exist sort of simultaneously, and one could be exchanged for the other. If you understood that, you could actually get this answer without doing the optimization problem. But anyway, we're basically just canceling out the reactance to maximize average power consumption. So this is the condition to maximize average power. If this condition does not hold, then you're not going to be drawing maximum power, and you cannot apply the formula to find the maximum power. And the formula to find maximum power is this. It's the maximum power is I haven't memorized it. Okay, it's this. And this is another thing, another point that I want to make out is, you see your power max is equal to V Thevenin. Realize this is a power. Can power be a negative value? Is there any chance power can be a negative value? No. So real power consumption, real power that you draw out from a circuit cannot be negative. So hence explains why there's an absolute sign. And then there's resistance. Forget about reactance. Can resistance be a negative value? That's the question I'm asking you guys. No, it's always positive, and hence that's why you have 8. This actually makes sense. And to find this relationship is not actually very difficult. If actually you apply R Thevenin is equal to RL and X Thevenin is equal to negative XL, and you apply this into you plug this into the optimization problem, you can indeed derive this formula. Okay, so another way of saying R Thevenin is equal to R of the load and X the reactance of the the Thevenin reactance is equal to the load reactance. Another way of saying this is just to say Z Thevenin is equal to the conjugate of Z load. And this is interchangeable. So you can say the Z load is equal to the conjugate, which is the same thing as saying Z load is equal to the conjugate of Z Thevenin. This is the same thing. So another way of saying this statement is saying that. So now we're just going to have a problem that asks us to find the maximum power of the circuit that we covered before. So for the circuit that we covered before, we know that the voltage Thevenin was indeed 37.95. This was, I think, 20.31 degrees. And the Z Thevenin was 6.48 minus 2.64 J. This was what we covered. This applies to the previous problem. And now the question is, how can we find the maximum power as seen from these terminals, as seen from the load? And remember, this was indeed A and B, as we did before. This was A and this was B. These are the reference points. So how do you draw maximum power? So what's the initial condition? What's the condition for this to happen? Does anyone know again? What's the relationship between ZL and Z Thevenin for us to maximize the withdrawal of average maximum power? What's the condition? That's right. So the Z Thevenin has to equal the conjugate of Z load. So another way of saying it, doesn't make a difference where I put the conjugate. I can put the conjugate here, let's say, for example, and I want to find what's ZL. In this case, to find ZL, what's the conjugate of this guy? What's the conjugate of Z Thevenin? Exactly. So I'm just going to write down 6.48 minus 2.64 J, all conjugate. A conjugate just says go into your expression and find, anytime you find a J, take the negative of it. So in this case, it's going to be 6.48 plus 2.64 J. So this is the critical condition required to draw average maximum power from the circuit. This has to hold. Once this holds, then now you can find the maximum power using the formula. The formula, again, was P max was equal to V Thevenin over 8R Thevenin, and this is all squared. And again, all the values are indeed positive, which is consistent with our understanding of what real power is. So the resistance is positive, and the V Thevenin, we're taking the absolute, which makes sense because we're dealing with a complex number. The complex number indeed here was 37.95. You realize this, there could be a negative in front here, which could be adjusted with the argument of the complex number, but as is, somebody could think that's why we have this absolute. That's why it's seen in the equation. So in this case, taking the voltage, the modulus squared, this guy, if I take this guy and I square it, is when that's going to give me the V Thevenin. So then I'm going to get is equal to 37.95. I told you this could be indeed a negative, so it's taken care of by the square, and then you have the 8. The R Thevenin comes from this guy, because this is, again, this is R Thevenin, and then this is X Thevenin. So yeah, X covers the negative, so this is actually J. So this is the another way of saying it. So we're just taking 6.48, plugging it here. I don't know, what do you guys get when you do this? Does anybody have any idea? 27.78? Yeah. Okay. So what's this value? What do you measure it in? What's the unit? What's the SI unit of this value, of this entity? Does anybody have an idea? We're dealing with power. What's power measured in? Watts. So this is our final answer. So under this network, we're able to extract the power of 27.78 watts, again under the assumption that the Z load is equal to the conjugate of Z Thevenin, which is the maximum optimization condition to withdraw maximum average power. Okay, and I believe that concludes the end of the tutorial. Thank you for listening.